Welcome to this episode of the CompTIA Tech Plus Prepcast by baremetalcyber.com. Let's begin. The information technology concepts and terminology domain is the foundation for the CompTIA Tech Plus exam FC0-U71. It makes up 13% of the total score, but its importance extends far beyond that number because the concepts here are referenced in every other domain. This section focuses on computing basics, the notational systems used to represent information, common units of measure, and the structured methodology for troubleshooting. Mastering these areas will not only help you answer questions in this domain, but will also give you a stronger grasp of material across the entire exam. The role of IT fundamentals and certification is to provide a bridge for learners who may not have a technical background. Domain 1 introduces the vocabulary, measurements, and concepts that appear later in areas such as infrastructure, applications, and security. Becoming familiar with these terms early in your study helps you read and interpret exam questions more accurately. Just as importantly, the same knowledge will make it easier to solve real-world problems once you are in a technical role, because you will understand the language and logic used in IT environments. The first exam objective, Computing Basics, introduces the essential model of how computers function. This includes the flow of data through the four main stages of input, processing, output, and storage. These principles apply to every computing device, from desktop computers and mobile devices to embedded systems. By understanding how each stage works, you can explain not just what a device does, but how technology as a whole supports user needs and business processes. In a computing context, input refers to any data or signals received by a computer from external sources. This can be as simple as a keystroke from a keyboard or as complex as environmental readings from sensors in an industrial system. Input is always the first step in any digital workflow and determines what the system will process next. Recognizing different forms of input will help you categorize devices and understand how they interact with the rest of the computing cycle. Processing is the second core function in the computing model and involves interpreting, transforming, or calculating the input data. The central processing unit, or CPU, is the primary component that performs this function, following logic, mathematical operations, and control instructions. The specifications of a CPU, such as speed, number of cores, and cache size, affect how quickly and efficiently tasks are handled. This is true whether the processing is happening in a personal computer, a server, or a network device. Output is the third stage in the computing process and refers to the delivery of processed data back to the user or another system. This can take the form of visual displays on monitors, audio output from speakers, printed documents, or even signals transmitted over a network. Output devices complete the cycle of interaction between the user and the system, turning the processed data into something that can be understood, acted upon, or stored. The role of storage is to retain data for immediate access or for long-term use. Storage includes both volatile memory, such as random access memory that is cleared when the device is turned off, and non-volatile storage, like solid-state drives and hard disk drives, which keep data even when powered down. Storage is what enables computers to hold operating systems, applications, and user files. Understanding how data is stored and accessed is essential for configuring devices, planning capacity, and ensuring that systems perform reliably. The second exam objective in this domain is notational systems. This section focuses on the number systems used to represent and work with digital information, including binary, decimal, hexadecimal, and octal notation. These systems are fundamental to computing because they are used in programming, memory addressing, and performing calculations at the system level. Being fluent in these systems and in converting between them is an important skill for troubleshooting and interpreting technical data. Binary notation is the foundation of all digital computing, using only the digits 0 and 1 to represent data. Each binary digit, or bit, can represent a state of on or off, true or false. These simple building blocks are combined to represent numbers, letters, and instructions. Understanding binary is essential for interpreting low-level operations, working with system settings, and decoding certain technical readouts. Decimal notation is the base 10 number system we use in everyday life, and it is often the most human-friendly way to represent numbers in computing contexts. Computers frequently convert binary data into decimal form for display to users. You will see decimal values in many areas of IT, from IP addresses to performance measurements like network throughput. Recognizing decimal values in technical contexts helps bridge the gap between what the computer processes internally and what the user needs to understand. Hexadecimal notation, or hex, uses a base of 16 with digits 0 through 9 and letters A through F representing values. Hex is often used because it can represent large binary numbers in a compact and readable format. It appears frequently in memory addresses, color codes for web design, and system log files. Being comfortable with hex allows you to interpret system-level information more quickly and with fewer errors. Octal notation is based on 8 digits from 0 to 7 and was more common in earlier computing systems. While it is less widely used today, octal still appears in certain legacy systems, file permissions in Unix and Linux environments, and specialized scripting contexts. Understanding octal ensures that you can work with older systems or specific tools that still rely on it. Finally, conversions between notational systems are a skill you may be tested on. You could be asked to convert a binary value to decimal, decimal to hex, or any other combination. This ability is useful for tasks like troubleshooting low-level hardware problems or reading system diagnostics. Practicing conversions, either manually or with the help of tools, will reinforce your understanding of how these number systems connect hardware and software logic. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. The third objective in Domain 1 is units of measure in information technology. These units describe the size of storage, the rate of data transfer, and the speed at which processors operate. You will see these values in almost every area of IT, from configuring hardware and comparing devices to troubleshooting performance problems. Understanding these units is critical because exam questions may ask you to choose the correct measurement, compare two values, or interpret technical specifications. Knowing what each unit represents helps you make sense of both theoretical questions and practical scenarios. Storage units are used to describe the capacity of a device to hold digital information. The smallest unit is the bit, followed by the byte, which is equal to 8 bits. Above that are the kilobyte, megabyte, gigabyte, terabyte, and petabyte, each representing a larger capacity by a factor of roughly 1,000 in decimal notation, or 1024 in binary notation, depending on the context. Familiarity with these values will help you evaluate storage devices, understand memory requirements, and plan for system expansion. Throughput units measure how quickly data is transferred over a network or between devices. These are typically expressed as bits per second, kilobits per second, megabits per second, or gigabits per second. Network speeds advertised by Internet service providers, the performance of network interface cards, and the capacity of switches and routers are all specified using these units. Correctly interpreting throughput values helps you select the right hardware for the job and diagnose slow network performance. Processing speed is another key measurement, usually expressed in megahertz or gigahertz. These values describe the number of cycles a processor can complete in 1 second. While higher numbers generally indicate a faster processor, other factors, such as the number of cores, cache size, and architecture, also play a role in performance. Understanding processing speed allows you to compare computing devices accurately and match system capabilities to user needs. Comparing units across different use cases is a common skill in both the exam and real-world IT work. For example, storage capacity is measured in gigabytes or terabytes, while processing speed is measured in gigahertz and network speed is measured in megabits or gigabits per second. Mixing these units or misinterpreting them can lead to incorrect conclusions during troubleshooting or procurement. Being able to clearly distinguish between them ensures accuracy in both study and practice. The fourth and final objective in this domain is troubleshooting methodology. This objective outlines a step-by-step process for identifying and resolving technical problems. It is used not only in technical support roles but also by engineers, system administrators, and security professionals. Following a structured approach ensures that problems are resolved efficiently, consistently, and with minimal disruption. This same framework is applied in other CompTIA certifications, making it a valuable skill beyond the Tech Plus exam. The first step in troubleshooting is to identify the problem. This involves observing symptoms, collecting information from users, and documenting the behavior of the affected system. You may reproduce the issue to confirm its scope and gather more details. A clear definition of the problem sets the foundation for the rest of the process. Skipping this step often leads to wasted time chasing irrelevant issues. The next step is to establish a theory of probable cause. This is where you apply your technical knowledge and experience to suggest potential reasons for the issue. You might start with the most obvious or common causes, consider recent changes to the system, or focus on components with a known history of failure. If you are unsure, you can consult documentation, online resources, or colleagues to help refine your theory. The goal is to narrow down the possibilities logically. Once you have a theory, you move to testing it. This involves applying safe, reversible changes or performing diagnostic steps that can confirm or rule out your hypothesis. If the test confirms your theory, you can proceed to the next step. If not, you return to your list of possible causes and try again with a different theory. This iterative process helps ensure that the solution you apply addresses the real problem. After confirming the cause, you create and implement a solution. This means developing a plan that resolves the problem while minimizing the risk of causing new issues. You should consider safety, system integrity, and clear communication with the user or customer. Having a rollback plan is important in case the fix introduces unintended consequences. Once you apply the solution, monitor the system's immediate response to confirm it is working as expected. Verifying full system functionality comes next. This step ensures that the problem is resolved and that the system works correctly under normal conditions. It involves testing user workflows, checking related systems, and confirming that there are no new issues. You may also apply preventative measures at this stage to reduce the chance of recurrence. The final step is to document findings and lessons learned. This includes recording the nature of the issue, the resolution steps you took, and the outcome. Documentation supports future troubleshooting efforts, helps other team members learn from your experience, and can be valuable for audits or compliance requirements. It also provides a reference point for identifying patterns or systemic issues over time. In the next episode, we will dive deeper into computing basics, focusing on the 4 key functions of input, processing, output, and storage. Understanding these in detail will strengthen your grasp of how computers operate and prepare you for related objectives in other domains. We will also look at real-world examples of each function and how they appear in exam scenarios. Thanks for listening. Please visit baremetalcyber.com for more cybersecurity information and education, including a new children's series. For more information on books and more, follow us at cyberauthor.me.